Hello, this is the PaveCo team, and today, we will illustrate our refinery's design that's focused on producing polymer-modified asphalt binders for road pavement. Are you tired of seeing Calgary's roads full of cracks during the winter? And hope that one day they will be as good and flawless as Regina Bypass? Because your answer is a yes, the solution is this polymer-modified asphalt binder. Our main project driver is the growing market for asphalt. As mentioned before, regular paving asphalt doesn't withstand extreme weather conditions and requires constant maintenance until replaced by new pavement. Thus, the PMA product is being researched and produced by multiple academic institutions and vendors, respectively, in different parts of the world, which brings us fruitful opportunities on the horizon for the future. Therefore, it's safe to say that asphalt demand is rising until 2030. This makes our product economically stable and viable for the future given the constant global need. Presented here is the block flow diagram for our process, which shows how we produce the polymer-modified asphalt binder. Starting off our main feed stream, which is cold lake bitumen, which contains salt that will be removed by passing it into a desalting unit. The desalted crude will then be heated and sent to a crude distillation unit, which separates the crude into different components. And the main product of this unit, which is the atmospheric residue, will then be drawn from the bottom of the tower to be pumped to a vacuum distillation unit, which separates the residue even further into lighter and more concentrated heavy components. And again, the main product of this unit is the vacuum residue, which is also drawn from the bottom of the VDU, and to be fed into an oxidation unit, which basically remove light fractions from the residue by blowing air to it. And finally, the oxidized residue is then mixed with SBS polymer in the polymer blending unit to produce our main product for our process, which is polymer-modified asphalt binder. The desalting unit. The goal of this unit is to remove impurities in the crude. It also induces an electric field to promote the coalescence of the water-oil emulsion droplets below a critical diameter to coalesce to criticality. At the critical diameter is when droplets can separate effectively via gravity. Anything below would be too stable to separate. Why an electric field is used is because of the polarity of the water, which can be used to direct the emulsion to coalescence. The crude distillation unit, CDU. The CDU separates our crude into different cuts based on their different boiling points. This will yield useful byproducts like kerosene, diesel, and gas oil. The produced atmospheric residue at the bottom will be further processed in downstream units. Our optimized design includes a column with 50 sieve trays and 36 meters in terms of its height. The vacuum distillation unit, VDU. The heated atmospheric residue enters the vacuum distillation unit for further separation with no thermal cracking of components. The 13-stage column comprises the use of bubble cap trays for the stripping section and random packing in the rectifying section to minimize the pressure drop per tray, instead of using bubble cap trays for all stages, as well as a demister pad on top to trap the entrained mist from the rising gas phase. We also decided to use 3 stages of steam ejectors at the top of the tower to produce a rough vacuum of 10 to 40 mm mercury. As evident from the diagram shown, the column's diameter varies to maintain a constant space velocity of the gases due to low pressures. To know exactly how the vacuum is produced, let's first recall Bernoulli's principle that shows the inverse proportionality between a fluid's velocity and pressure. Steam acts as a motive fluid and is accelerated into the suction chamber, where it entrains the VDU off gases due to the low pressure, hence creating vacuum in the VDU itself. The gas mixture gets compressed in the diffuser, then passed to a condenser to separate the condensed steam in order to ensure regular operation in the next steam ejector. The oxidation unit. The vacuum residue is first preheated by passing it through a furnace and a heat exchanger. The short residue is introduced into the blowing tower. Air is bubbled through the bottom of the reactor. The exothermic oxidation reaction increases the apparent molecular weight and polarity of the asphaltene. This in turn stiffens the asphaltene, decreases its penetration, and increases its viscosity. This makes for more durable asphalt for paving and extends its lifespan. The contact between the asphaltene and the oxygen is improved by using a mixer in the oxidation of the asphalt. The polymer blending unit. The purpose of the polymer blending unit is to mix the SBS polymer with the unmodified binder. This is the final touch to our product before it's sent for storage. The process adjusts the rheological properties of the binder, making it more resistant to permanent deformation and cracking, providing better long-lasting roads that require less maintenance. The unit is composed of a cylindrical vessel, an agitator connected to a shaft that rotates the mixing blades, and a heating coil to provide heat. Lastly, baffles are added to the side of the tank to prevent the mixture from causing swirling in order to avoid inefficiency. The University of Malaya conducted a dynamic shear rheometer test to evaluate the effect of mixing time on binder rheological properties. The dynamic complex moduli versus time at different temperatures was tested and plotted. Steadiness of dynamic complex moduli indicates consistency, meaning the mixture is homogeneous. The experiment found that a mixing time of about 30 minutes, an operating temperature of 180 degrees Celsius and speed of agitation of about 2,500 RPM are required to complete the mixing process. We've designed our polymer blending tank to process about 130 cubic meters of material per batch. The actual volume of the tank is 162 cubic meters. The tank has both a height and diameter of about 6 meters. Other important design parameters are presented in this table. From the construction of this plant, we can expect more employment opportunities within the Albertan market, while also diversifying the energy sector for the province. One aspect of the plant that requires high attention is the fired heaters used to preheat the stream feeding the CDU and VDU. In the case that the heaters experience ruptures, they can cause an explosion. We plan to mitigate this by controlling temperature to degrees that the piping and walls can handle, as well as addition of constant inspection over the VDU to avoid air from entering. Environmentally, one key issue is our sour streams. We plan to send any sour gases to vendors to treat via hydrodesulfurization and Claus process. Any sour water will be similarly dealt with. Thanks for watching our presentation, and we'd love to hear your questions on April 13th between 10 a.m. and 12:30 p.m.